Hello. I hope you can hear me, right? Okay. So we are still stuck with him in this planet, not going anywhere so far. So I am Tawfiq. I am actually an aerospace engineer, but I'm working as a scientist for German Aerospace Center. Actually, he already mentioned this, like NASA of Germany. Yeah, so that's how I would put that, because we are still working a lot on our marketing side. So let's see. So today I'll be talking about how we actually work on designing aircraft digitally, mostly actually, because I will go through all the phases, how we used to do that, and now what we are doing right now. So maybe a very brief information about German Aerospace Center. So this is the National Research Center of Germany. We mostly work on the aeronautics and space, and we have more than 10,000 employees and 55 different locations within Germany. I think we have more than 60 institutes so far, which is located in different parts of Germany right now. We're not only working on aeronautics, we are also working on space. Like, if you remember the Ariana, how many of you are kind of familiar with rocket launches? Like, that's awesome. So we actually support quite a lot of technology for international space stations. And also, if you remember the Ariana launch, we actually took part a significant part of this technological side from the DLR side. So we also work on transport. It's just kind of, you'd like ask, why do you guys work on transport? We are in a space agency or so, but yeah, it's the technology. We have no bounds. Also, we work on energy sector, like designing new wind turbines, also solar energy, whatsoever. Also, we work on security a lot, like data security and also cyber security and other like physical security stuffs as well. And mostly, yeah, digitalization, that has been a big part of this whole DLR, I would say, path for the future. So, as I have mentioned, in DLR, we have more than 60 institutes. So this is one of the institutes located in Hamburg, where I work. It's the DLR Institute of System Architectures in Aeronautics. So basically, we explore. So the mission of our institute is that, as you can see, that there are lots of different data and the technology is moving very fast. So we have to find a way to integrate all of them together to create a digitalized version of the whole aircraft design workflow. So this is what we do. So basically, we call it a digital thread. I will explain it a little bit later. And the scope is like a collaborative digital engineering methods for system architecting. And also, we try to pre-design all the aircraft models before it goes to the physical phase. And also, we work on cabin design and industrialization of the technology we create. And the methods we work on, I don't know how many of you are familiar with model-based system engineering? Anybody? Okay. A little bit? All right. Also, multidisciplinary design optimization. Okay, no, but it's a term for system engineering most of the time, but we also use it a lot. And mostly we work on also virtual reality for digitalization of the cabin design. So we have a group inside our institute. They create new designs of the cabin, and then they implement it through the VR. And you can basically see the whole cabin using that one. That was really cool. So one of our colleagues, actually, he's using that one right now. And what you see right there. So also, we have this another concept. It's called system of systems engineering. I don't know if you are familiar with that. So we consider every system as a system. Like, for an example, if you consider airport, so airport combines with a lot of different systems, like aircrafts, I don't know, some fuel system, maintenance blocks. So we combine all of them. So we consider each system and create a system of that systems. So that is called like SOS in short. And of course, as artificial intelligence, it's like we try to implement everywhere, wherever it makes sense, mostly machine learning. Sometimes it's surrogate models or some probabilistic models for different parts of the data workflow. And also we do a lot of code designs and also robotics and so. So first of all, what are the different fields actually we are interested in our institute? First of all is aircraft concepts. So before we create an aircraft or design an aircraft, we have to find out a different version of that aircraft and find out which one makes the most sense for the specific mission. So this is one of the most important topics we work in our institute. And second one is a zero climate impact. So whatever we are designing, it shouldn't have any climate impact, like in terms of carbon or emission whatsoever, you know. And the last one is the system integration. So for an example, here you can see that we are researching on implementing different hydrogen capsules inside the aircraft. So it's like a future version of fuel, because as you know that at some point we'll be running out of fossil fuel. We have to find a way to actually replace that thing. And one of the most promising technology we have is hydrogen. So we work a lot on the hydrogen tanks and hydrogen integration into aircraft and try to understand how it works before actually we go on prototyping of the aircraft. And also certification, like, okay, you're done, now what do you do? Like, who gives you the permit? Like, so this is what we do actually. So, and secondly, we also perform not the physical manufacturing, don't get me wrong, it's digital manufacturing. So basically we design how it might look like when you go for manufacturing phases, and also integrated cabins, like it's not only from outside, we also integrate the cabin inside the aircraft and see, okay, does it make sense? Does it fit well with the design we are creating or so? Also, design explain. So explain is basically a different kind of airplanes which are not conventional. Well, the planes you see mostly have like two wings, one like a vertical tail, and you see like a basic shape, right? It could be something like that as well. So that's another part of the research we do, because it might be most like a convenient one for the specific mission or so. Also, sector coupling is another part. It's like as I have mentioned once, think about the like an airport, where you have different systems and you have to understand how you want to implement all those together. So we have a specific group. They work on system of systems. What they do, they simulate an airplane, like an airport, how it looks like. They run it through the whole thing, like airplanes are coming down and going out. It looks kind of easy, but when you think about like thousands of flights in a day in an airport, and you have to think about the energy and also the maintenance, also the fueling system, also the passengers incoming and outgoing, it becomes quite complex. And also the defense. I cannot talk a lot about the defense anyways, but you understand, right? So, my first question, do you have any idea how we design an aircraft, or how to design an aircraft? Anybody? Maybe the first phase. All right, I give you a task. Okay, you have to create or design an aircraft. What do you do first? Very good, very good. Yes? I think that's a very good. Yes? Like a base model and then continue. Yeah, actually, all of those answers are correct. Even the ChatGPT was correct. But so, before we introduced the digital era, this is what it used to look like. So first, we talk about the conceptual design. So can you imagine the engineers were like designing the aircraft with the pen and pencil on a paper, hundreds of thousands of engineers together before like a digital CAD system was introduced. So this is the first part, conceptual design. I'll go a little bit detailed in the next slide. The second one, we designed the preliminary version of the aircraft. What you do is like the first one is that we solve the basics of the aircraft. We look at the requirements, then we solve the physics of the airplane, then we decide, okay, what it should look like or so ever. Then you create a small model and put it in a wind tunnel. Then you get the data. If you're satisfied, then we go for the detailed design. So we create the detailed design of the whole airplane, and then we create a prototype, and then we fly, and then we see, okay, how it looks like, whatsoever. So kind of dangerous for a test pilot, though, but yeah. For engineers, we just say, it didn't work. Huh? But for a test pilot, so let's go a little bit detailed. So first one is the first phase of a conceptual design. First, what you do is just you derive all the requirements, all the external derivatives or so. Then you solve the flight physics, like how it should fly, how far it should go, how long it should stay in the air, blah, 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 how many people will be there in the aircraft or so. And also, you do the new assessment of new technology. This is a very important part because designing and like from the starting of designing an aircraft to the end, the whole life cycle could take decades. Like the models you see, I think I have seen somebody from Airbus here. We just met, I think. All right. So it takes around a couple of decades, like from the starting point to the last point. So you have to also consider the fact that within this 10, 20 years, the whole technology might change. So that's another important part you have to think about. So we also assess that part in the conceptual design. Second one is a preliminary design. So what you do is like, now you decide, okay, now I have all the calculations done. I have decided what it should look like whatsoever. Now you design it. You create a small model. You put it in the wind tunnel testing. You then test it for different ranges, like before, like with different altitudes of the atmosphere, all right, before. And then you get the data, you validate your calculation, so it works like a cycle. And then when you're satisfied, you say, all right, let's do a detail phase. Now the test pilot comes here and say, let me try it. And if we are all lucky, it will fly nicely. So this whole thing actually is kind of a loop. But when you are done with the loop, you come up with the design freeze. So you just freeze that phase. You don't touch it anymore. That's the whole part. Otherwise, it would be like a never-ending loop, right? So what we do actually, our main part is to like optimize that conceptual design part so that we can minimize as much error as we can before we go to the other phases. Because think about finding some errors here and also here. Why, you might ask, like, why not like optimize this part before this one? Actually, we all optimize all these phases, but the thing is, in the preliminary design part, is very expensive and time consuming. And this one is like life-threatening. So you have to focus a lot on the conceptual design so that you can come up with all the solutions of all the possible problems. All right. So now the question is like, what if, as I have shown you the pictures of where all the engineers were drawing on the papers or so. Now is the new era. So it's now, what if airplanes could be designed digitally first? So before we move on to that physical phases, right? So why digital? Any idea? Why we should go for digital design? Cheaper? Faster? Reusable? Yes? Safer? Verifiable? Very good. I think, yeah, they're all correct answers. So it's like faster. It used to take like months. Now we can do like within minutes or hours. Now we can do 100,000 or millions of simulations before we create a prototype. So it's like very, very cheap right now. And also we can find the errors before we go to the next phase. It is sustainable aviation. So we have to find a way that, okay, this aircraft design is not producing a lot of carbon or whatsoever, right? And then we can experiment a lot of things. Like we can optimize the design, we can change the design and see how it works or so, but which is not kind of possible in the physical phases, like which is preliminary design and detailed design. And also we can connect all the systems. The systems means like if you think about the cabin, the aircraft itself, the fueling system, the other control algorithms, or the engines or whatsoever. And also, you have a larger design space. That means you can explore, like, I don't know, hundreds of different airplanes, and then pick one, which is the optimized one for that specific mission. So which is kind of, so all these benefits giving us a lot of independency to actually explore and experiment. So how do you build a digital thread? So digital thread looks like this. Not this yet, but it's coming. So this is an aircraft with all the systems inside the aircraft. First of all, we do digital engineering. So what it is actually, right? So it combines all the different phases. For example, digital engineering combines climate impact, the manufacturing phases, the industrialization, system integration, certification all together. So actually, it gives you, as you can see in this like a small slide, there are lots of different workflows there, like lots of different parts. So those are actually different parts of the whole digital. So these are all coupled or tied together in a digital thread. So if you run it once, the idea is that you will get all the information, what it might happen through the whole life cycle of the aircraft design. So in our digital engineering process, how do we approach this problem, right? First of all, we define the problem. So as I mentioned, that what is the problem? Let's say somebody comes very rich, saying that, okay, I want you to create an aircraft that can fly, I don't know, 20,000 miles, all right? So that's the problem definition. So you come with the stakeholders and the needs, like the requirements. What do you need? What do you need? What do you need? And who are the customers there? And then secondly, you decide the system specification. So basically, so first one was the mission requirement. This one is the system requirement. So basically, how my aircraft should look like. Second phase of the problem. Third one, system architecting. So you have the requirement from the stakeholder, then from the aircraft. Third one is that, all right, now we have to design a couple of aircrafts and see what is the best one. And the fourth one is a system design and optimization. So now you have the designs. Now you optimize the whole system to make it the most possible design spaces for that problem, right? And then the last one is system solution exploration. So what you do, you trade off different models. You choose one. And this whole process comes up with an aircraft. So as you can see, like all of these phases, they are kind of interlooped within each other. So basically, they are giving feedback for after each loop. So it's a very optimized way of designing the whole process, because in each phase you can find the error and you can reduce it before you move to the next phases. So let's get a little bit deeper what you do actually right now. So you have the system identification, specification, architecting, synthesis, and exploration, right? So now, this whole part, we call it system definition. So the requirement from the stakeholder, also the requirement from the mission, we call it system definition. Second, we call it system architecting, so system definition, system architecting. And the third one is system MDAO. So MDAO is multidisciplinary design analysis and optimization. So basically, we analyze this whole phase and optimize it. So in general, we call it like the three different phases of the design problem. And this is the upstream architecting, and this part is the downstream architecting. And this whole process is called MBSE, MDAO development system. So model-based system engineering and multidisciplinary design analysis and optimization. So to face this kind of problem, this whole process in the DLR, we have this collaborative MBSE MDO framework where we have developed multiple tools to tackle all the data that has been passing through all those different phases. So I'll be talking about with the tools that are open sourced, so publicly available. I cannot really talk about all the other tools that are in-house. So so this is like an overview what we do for different phases and when you design an aircraft. So that was like a whole overview of the aircraft design. Let's get to the point now. So designing aircraft is an ultimate data problem. Why? So like this is an aircraft, and as you can see, how many different disciplines are involved there. It's like, how do you handle all this data? So each of these plots or pictures actually representing each institute, maybe a different organization or maybe a different company, which makes it way more difficult. Because if you're designing the whole thing within your one company, then you find a way. But it makes it way more complex if all the different industries, institutes, or research organizations are working all together to solve one problem. I don't know if you have any issues, like if you have meetings in different time zones. I don't know if you guys are experiencing this kind of problem, like somebody is from the US, somebody is from the UK, somebody is from Japan. How do you handle that? So that is only for meeting. Think about this kind of data. So now, without the proper data management system, what happens is that, so the guy said, all right, I have this data, I have my own format, I send it to you. He says that, all right, I have my own data, I have my own format, I'm sending to you. And look at how it looks like. It's like without proper data management, it goes like it booms out. So it's like you have total number of different format is n times n minus 1. So that's like a huge number. So now that was a huge issue at the very beginning when we started working together, like a collaborative design problem in our institute. So we had to find a way to actually create a data model that would be both machine readable, also human readable, and also passable. Like you can pass that data model to somebody else. Don't think about it as a database or something. It's like a data model. So it's like a language, finding a common language. So for an example, if you can compare with the real life, somebody speaks French, somebody speaks, I don't know, some other Latin, somebody speaks Chinese, somebody speaks Japanese, then they would have like a real problem when they communicate with each other. So we had to find a common ground within all these different disciplines. So what if we had this like a same language for every discipline? And then we can reduce the total number of different formats or the issues by a significant number, by 2n. And we call it Common Parametric Aircraft Configuration Schema, in short, CPACS. So CPACS is a language for passing it from one discipline to another. So to be honest, it took a long time to manage that because it means that all the institute had to say yes for this data format. It took around 7 years to just come up with this data model. So a lot of work. So CPACS works as a single source of truth. So basically, you put all the data related to the aircraft design in that file. And this is open source. So any interested people who wants to go through the tool or the language system, you can copy that one, go to the website. It's like open source. They have you can also join the community there. So this is one example. CPACS is basically for aircraft design, but you can also come up with some new data model for your own purpose as well. I will talk about it later. So how it looks like. So here you can see that, okay, we have CPACS has two different data formats. One is XSD, other is XML. So XSD gives you the schema. Schema means the rules and regulations on how you write the data. And the XML is the format where you write the data. So XSD is the rules and regulations, and XML is how you write the data. So as you can see, this is a format of an XML file. Here you can define the fuselage of an aircraft. You can define the wings of an aircraft, like the engines, then the landing gears, and then the analysis results if you had somebody. So this could all be coming from very different institutes or organizations. But they could put their data inside this file, and everybody would understand. That was the whole purpose of CPACS. And it goes hierarchical structure. So like a top level, second level, third level, it could also go deeper, but I didn't put it there. And also, with this thing, you can do parametric analysis. So you have couple of fuselages there. You have a couple of wings there. You have a couple of different engines there. So you can just put them all together and come up with many different models. And then it actually helps you out to explore the right model you need for the mission. So how it works? So as I'm saying, okay, there's one schema file, XST, and we have this XML file. So we have this XML processor that actually validates whether your XML file is okay or not. And then you come up with the documentation where it shows, okay, this is how it looks like, or this is how your data, or whatever. So this is how it looks like, I mean, in the CPACS format. And all right, so next tool is kind of cool. Now, so all these things happens in the file, right? So how do I know what it looks like after putting all the data in the file, right? So we had to come up with a tool that actually gives you a 3D version of the airplane from the data model, right? So this is called TiGL. So also it is also open source. If you are interested, you can also check and be a part of the community, also help developing it. So DLR is a strong supporter of open source tools. It tries to involve all the academia and the industry together to come up with some brilliant idea. So a very short example how it looks like. So you just drag and drop your CPACS file and you could see the whole aircraft. So anything you change, so there are different files you can come up. So maybe you have worked on some different files or so. You just drag and drop and see how it looks like. Change the I don't know, wings, change the engine, and see how it looks like. So this is actually was very important part, because by looking at the data, you have no idea basically how it might look like, right? So we had to come up with a way that, okay, that will give you the impression, okay, how your data is looking right now. So next one, now we have the data. Now we have, okay, convinced everybody to use that data model. Now we can see the data. So now the important the problem is that how we work all together. That was another issue. So it's like we have one partner, I don't know, in Bremen, another partner, I don't know, in where, Stuttgart maybe, another partner in the UK, another partner in the US. So we had to find a way to work all together in the same workflow. So basically, let's say the partner A is providing the engine, partner B is providing, I don't know, the whole structure, partner C is the software, partner D is the, I don't know, cabin. Now we had to find a way so that all those tools could be integrated in the same system and work simultaneously all together. So that is when we came up with this software called Remote Component Environment, RCE in short. It is also open source, by the way. You can use it for your, so basically it's not only for aircraft design, you can use RCE for any kind of workflow automation. Like, it doesn't matter. It could be in medicine. It could be some other fields as well. So RCE is very, I would say, you can modify it as your own use. So just use any kind of language or any kind of tool, implement it, and see the results in the automation. It's open source, free, so kind of cool. And this is how it looks like. It's not really super cool, like, I don't know, a commercial look. But as you can see, like here, you have TiGL viewer, and here all the analyses are working together. So for an example, thermodynamics analysis, there's some trajectory working. There's optimize the aerodynamics whatsoever. So they all work together. And as they work together, you can see the simultaneous change in the geometry. When it's running, it's really cool, actually. And yeah, so this is like an overview of how it looks like, the whole RCE. I wanted to show like a video, but it took a lot of like different architecture work to do that. But it's open source. You can download it and use it by yourself. So why? What are the things you could do with RCE? First of all, is integration. You can do, like, you can integrate your tools, any kind of tool, in the RCE pretty easily. Second one is the data management. If you are into the data, what is going on, which data is going to which tool, how is going, what is my like output, or so you can also go deep and check all the data, from all the phases. And also you can automate your tools. Like from this tool would go to this tool, this data would go from here to here, and you can then automatize the whole system, so it would run automatically. And the fourth one is collaboration. This is one of the biggest one, because you had to find a way so that everybody could work together in the same ground. Otherwise, it was extremely difficult to work together. So this is actually the whole system looks like when you design something like in an operation way. So you have the CPACS data file, and here you have the whole process of the design file of the aircraft. You have the workflow, you can see the parametric studies, and you can see the whole view of the aircraft. So this is how it looks like when we work on some new conceptual design for any new aircrafts. And all right, so another cool thing is that we created this digital hangar. So we have worked on many different aircraft models, and we decided to put them for public. We just opened it up a couple of months ago. So what you can do, it is also open source, by the way. You can go to the website and check it out. So what you can do, like you can choose any model there and download the file, CPACS XML file. Then you can modify it, change it, play around with it, use RCE, and use TiGL to see how it looks like. So you have all ready-made aircraft models here. So, as I said, beyond aviation, so this whole process, like creating data model, then like putting them in the same environment for workflow, and then getting the data, analyze it, and pass it through the other organization. This whole process has been used for beyond aviation. It's like we use it in the space, we use it in the wind turbines, like energy sectors. You can use it for train design or vehicle, or I don't know, solar panel design, or maybe marine design architectures or so. Also drones. So these are the all fields DLR has been working on, basically. So it is like an universal Lego kit. So you can, I would say, imagination is the only limit. Yeah, just work on or come up with some idea and just try it out. And yeah, my question would be, what would you design first with this toolbox? So it's up to you. Thank you very much.